And yeah, we have also taken the video recording, okay, video recording for AV class, okay. So before 大概在周五结束啊，礼拜天啊 ，make sure before the Sunday, okay, because Sunday upload to the e-class. 我们现在有 e-class 嘛 ？We have an e-class right now, yeah. So you can get the link, okay. You can get the link. So just in case 啊，如果你没有来上课啊，因为是怎样啊，或者是你想要 record 一些课程的内容 ，OK， 你可以在这个video recording 啊 ，OK， 那我是吴志明哈，应该没有人不认识我了哈。那这是我的 email，OK，my email and office and this is my phone number，OK，mobile phone number， 好，你也可以记一下啊。And if you have any question，OK，this is my office hour，OK， office hour is welcome to my office， we can， 我们可以再讨论一下啊 ，OK。那我们的讲师啊，敦杰啊，在我们前面这一位啊，敦杰啊，要不要站起来？来，敦杰啊。好，那傻逼侠啊，就是主要是做 video recording 啊 ，mostly 啊 video recording， 还有约翰 ，OK， 陈思荣，哎，好，然后陈志，好，好，那我们的讲师跟那个助教群哈很多哈，所以一样啊，同学如果任何有问题，也可以问助教、讲师或者是我啊，那直接来问我也都可以哈，没有任何的 barrier 啊，不要任何的担心或什么的 ，OK， 可以吗？好，那上课的方式主要就是英文，这样 OK 吗？还是希望大家用中文，都可以嘛哈？哦，那就用英文了哈。我英文没有讲得很好啊，请大家包涵啊。但今天这个是 policy，OK， 但是很多重要的地方。或许讲完之后，我还是会用中文 ，because we don't have, because I also feel very strange. We don't have the international student. How come we had to use Chinese, English? But because if you look at about 因为我去交流过、交换过哈，所以我会觉得这是大概是一个潮流了，也不能说是一个潮流，我会觉得。因为你将来一定会碰到，将来一定会碰到，就是说，你可能未来进入的企业界，你可能未来到国外去念书，其实我觉得比例很高啊。那你必须要去了解用这一种共同的语言，就是英文啊，去接受到讯息，这个啊，去接受到这个讯息，然后你也可以 learning 啊，你也可以学习。那甚至 you can use the English to present 啊，去做一份很好的简报跟报告这个我觉得也是一个过程让大家理解啊。OK，Chapter One 其实没什么哈，Chapter One 大概是谈一些有关 Newton's Law 那这些 probability 那牛顿力学这个是 F 等于 ma kinetic energy 这个大家要知道一下这些这个 momentum combine 这些，然后光速这些 angular velocity Einstein 这个equation 那另外energy also can be write as this is a Planck's constant we call H 这边有一横，这个叫做 reduce the Planck's constant This is because of if we talk about the Schrödinger equation and we will derive the Schrödinger equation and this Schrödinger equation mostly we have to discuss about the energy, electron energy. Because we have to reduce the angular velocity, angular frequency, which has a 2 pi factor. 这边有一个 2 pi 的 factor. So reduced Planck's constant means h reduced Planck's constant is h divided by 2 pi 啊，就是说到这个薛定谔方程式的时候，我们都用这个 reduced Planck's constant。到薛定谔第3章、第4章，我们都只出现这个 reduced Planck's constant。那这个其实就是等于这个，知道吗？所以他把2派除掉，否则你的薛定谔方程式会一直多出一个2派，很烦呐啊！就是你在写那2派就会觉得很烦。所以到薛定谔方程式第3、第4章的时候，全部都是这个了啊。所以这个没什么啊，这个只能注意一下。OK， 所以你这个 energy 啊，E 就会等于也是等于 omega h 啊 ，reduce Planck constant 跟这个一模一样的啊。OK， 那 wave and particle duality 我们刚刚稍微有提一下了哈。那大家看一下哈，这个是什么形状？三角形，什么形状 ？circular， 圆形 ；square， 方形啊。你现在这样看的话，老师，这既不是圆形，也不是方形，对不对？你现在看到的全吗？如果我把你绑起来，啊 ，some student 哦圆形 ，some student 哦 square， 对不对？这个就是波的2元形 ，right？ OK，this is quite interesting。这个从这边投影变成是圆形，从这边投影变成方形，这个只是一个意象啊，就看你不是你就其实就你来听这我刚刚讲，就是在19世纪末的时候，人家在看到说哦，这个电子就是粒子，你的电子嘛，对不对？就是粒子啊，光子也是。粒子，对不对？孔子呢，既不是粒子，也不是波，孔子是我们至圣先师哦，孔子不一样。所以在那时候的时候，我们是很难去想象哦，就是说，electron 啊，既是光既是一个 particle， 也是一个 wave 啊，所以接着就像是在看着这个 object。We only focus on this part, okay? And if we look about this way, then it is a difference, totally different. So, if we talk about the wave, okay? Wave function, the wave function, usually we have 2 domains, okay? Wave you can use, for example, this is the wave function, which is the sine. And then it consists of the space domain and also time domain, right? So the space domain you can have, for example, if we look about this function, okay, a cosine and 2 pi over lambda x substituted by omega t, okay. This is the same as the previous equation, right? So 2 pi over lambda. Right here, you can see about here. 2 pi over lambda is equal to 2 pi and p divided by h. This is the de Broglie wave, wave function. Okay, sorry, de Broglie wavelength. Later, we will talk about what is the de Broglie wavelength. Okay, de Broglie wavelength. Just keep in mind. Okay. So. Here, if we look about this equation, 2 pi over lambda, it's k. K actually is the wave number. K 就是一个 wave number. Okay, wave looks like right. This is the wave, and this is a wavelength, right? So wave number k. It's 2 pi, this is 2 pi, right? Divided by lambda, right? So you have, if you have the difference wavelength, of course you get the difference wave number, right? So this is the wave number. So wave number is located right here. We get k is such omega t, okay? And Omega we know about E is equal to reduced from this constant and omega. So omega proportional to the energy, right? So here imply this wave function has energy value, right? Electron energy. This wave function is the electron energy. It's an electron wave function, and there is energy term. So this omega we call it energy term. 好，知道吗？哈，就是说这个地方它有一个时间的 domain 以及一个位置位置嘛，空间嘛，就是位置的 domain 它有2个 domain 那这个通常我们是在讲这个 position 那这个通常是在讲能量知道吗？能量这个地方我们讲电子的能量相关那这边会有不同的区间，所以 so you have you can create the different wave function. Okay. So what is the wave? Okay, disturbance. Okay, which is periodically position and time. Okay. 那这边be careful about this. V. This is V. Okay. Looks like very similar to mu. This is the mu. Mu is the frequency. This is the V. V is the velocity. V here 我们写在黑板我会写成这样，才不会被误会。V mu looks like and lambda 这样子。Velocity. Velocity means the wave. Okay, it's right here, right? The wave has a velocity. 它有一个波速has a wave velocity 那这边是跟这个频率有关and the wave function and lambda. Okay. So K is over to here. Okay. 所以你可以得到这个我想这个不需要不太需要讲Double slit experiment. Okay. Okay. So I will show you about the video, which is quite interesting. 因为今天第一节上课所以我想说下面有一个 video, which is quite interesting, 给各位看一下，大概10分钟的我们刚给看完之后，我们就可以下课那 this video shows which is the geography， 这个是一个国家地理频道这个国家地理频道拍的，我觉得蛮不错的。Talk about the quantum mechanics, quantum mechanics 量子力学this is quite 非常的科普and you can easy to familiar how electron can be treated as a particle and how electron can be treated as a wave 那它就是用一个 double slit experiment double slit experiment because 我大概先讲一下double slit experiment you can see based on this experiment we know here there's a distribution okay 它有一个分布它这个分布就会观察到就是说在中间的这个地方在中间的地方这个 particle 这个电子打到这边的密集度是比较高的is mostly highest 然后再一序是2侧所以这个地方我们就可以观察到就是 there's 这个 interference 它有干涉的现象就是因为有干涉的现象才被视为是这个电子是有波动的现象
certain motion of galaxies and stars and planets. But now we know, at a fundamental level, things are a lot more fuzzy. Because we've discovered a revolutionary new set of laws that have completely transformed our picture of the universe. From outer space to the heart of New York City, to the microscopic realm, our view of the world has shifted, thanks to these strange, mysterious laws that are redefining our understanding of reality. They're the laws of quantum mechanics. Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense. Until about 100 years ago, scientists were struggling to explain some unusual properties of light. For example, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected. If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared, complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
It was something of a mystery how to understand what was going on. An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase, quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron has to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
As mysterious as it might be, the evidence quickly mounted showing that Bohr was right. Electrons followed a different set of rules than planets or ping pong balls. Bohr's discovery was a game changer. And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics. One test in particular, which would come to be known as the double-slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double-slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing. Waves. Waves do all kinds of interesting things. Things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go? Our
Waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave. A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in an ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities. You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrodinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise. So long as you can accept that it's all about probability. If you think that probability means you're reduced to guessing,
Okay, so this is a video， 你可以看一下超乎想象宇宙哈因为有点长大家是45分我们刚刚看了13分。So based on the double slit experiment, so you I believe you understand about because the particle of the electron, okay, has an interference effect. So you can see about there's the screen, right? You have the probability of the wave, which means that the electron occur in a specific area, which probability will be mostly higher. 就是说，在哪个地方所出现的位置是最高。So Schrödinger equation is used to predict about the position of the electron. Okay, position of the electron, and also you can use the Schrödinger equation to understand about this property, the probability. Okay, so because we know about wave where we interreact and then produce in the furnace, okay, in furnace, because there could be this is a peak and there's a valley, right? So some of the wave will be cancel out each other, and then you can look at about finally if the wave reach to the screen, okay, here. Let's finish this slide, okay? You can look about this. This is a light source, right? Light source means that you have a thousand or billion of light particle, okay, float, okay. through this channel, okay, double slit channel, and then it create 2 light wave, and this 2 channel of the light wave will interference each other. So therefore, finally reach this screen, you can see, oh, here there's a dark and bright, dark and bright. This is just looks like 它有一个底片我们讲说是一个底片，所以这个底片在这边成像So you can see about here, okay. At this position, right? This is this 就是一个破坏性干涉okay. Destructive, okay, destructive interference, okay. So if we look at this point, there's no electron or no photon to hit this position. But if we look about here, mostly bright, because at this position, you can look about this is a construction interference. 那变成是到这里来说是变成是一个建设性干涉。So therefore, we can see about this pattern. Okay, we can look about this pattern looks like that, based on the double slit experiment. Pretty it's not difficult. Okay. Okay, so 我们大概这一节课先上到这里那我们想说这个在礼拜5我们再获取后面的课程。Okay. Any question? Okay. 好，这是第一节课